All right, folks, you know the drill. It's time for another Intrepid Sea, Air, and Space Museum Virtual Astronomy Live here. Juggling a lot today, but we do these shows once a month. I'm John Galloway. You may know me as DOS with the Kerbal Space Academy. But for the last, year plus, we've been doing virtual events once a month, the third Thursday of the month, talking to cool folks who have cool science stuff, space stuff, etc., to share with us. So today we're going to be talking about the James Webb Space Telescope. The flyer says James Webb Space Telescope launch. It's not actually launching today. That's coming up, but let's just hold a hand over that real quick so you don't see that it's launching. It is not launching today, but we are going to be talking with some really cool folks from the James Webb project. Of course, the James Webb Space Telescopes, or you can even really call it Hubble 2.0. It's like the next big space telescope that we are putting up in space. But we're going to give just a second here for the notifications and stuff to go out. You may have had the little spinning shield there for a second. Not something normal that you see on the other outlets if you're watching on Facebook or YouTube today. I know, right, Twitch? We're streaming all over the place today to help Intrepid share this with more people. But we are going to get going in just a minute here. We'll get a couple more people into chat just confirming that everything's working fine. Over there, Hydra and K-Rath over on Twitch, thank you all so much for hopping in early there. But again, time for another Virtual Astronomy Live. We'll be getting going here in just a second as soon as we give folks a little bit of a chance to file it. Again, talking about James Webb Space Telescope today, we'll have some fantastic people who actually work on the project's program manager and an engineer, a systems engineer on the project, and that's coming up in about 24 minutes or so, right? In the meantime, we're going to do our pre-show. Every month we do a pre-show and we talk with somebody very cool from the museum. So let's go just one more minute here and make sure that we are good across the board. I see it there, and I see it over there as well. I think that I see it basically everywhere, and it's looking pretty good. Again, doing a little bit different thing. Normally we do these shows on Twitch, but we decided that we were going to send them even more places. So you're wondering, you've never seen this dude who's on the screen before. I'm normally over on Twitch doing shows with the Intrepid once a month, and today we're putting it over on Facebook and YouTube as well. Just means I've got a lot more buttons to click. Good times. But let's see. It looks like everybody's saying yes. Okay, I think we're doing fine here. Let's go ahead and bring up our pre-show really quickly with our fantastic lead teaching artist, educator, etc., from the museum, Elysia Segal. How are you doing? I think we may have. Let's just.
Oh, good job.
How's that? We should be able to hear Elysia there. We good?
All right. Hello, everyone. Nice to be back.
All right. How are we doing today? I think we have a little bit of a pre-show here to go through.
That's right, as usual. So tonight's Astronomy Live, Astronomy Live is all about the upcoming launch of the James Webb Telescope. That's going to happen in the next few months, hopefully, that's going to help us look deeper into the universe. We are going to see some amazing images from there that are going to be even better than the ones that Hubble has showed us, which have, of course, really opened doors and answered a lot of questions that we've had about the universe.
Yep.
So very excited to be watching this launch eventually when it happens.
It's been a long time coming as well. Like, a lot of people have been following James Webb for quite some time, and it's finally down actually to the launch site. They shipped it down there on a ship, and they unboxed it at the launch site, started to put it up on that rocket that it's going on. So a lot of people have been waiting for this for a long time, right?
Oh, yeah, totally. And we at the museum are so excited for it as well. A lot of what we know and see of distant stars and planets, though, there's still kind of only what we are able to piece together from these just snapshots of data that we've gotten so far. So for my pre-show tonight, I'm actually going to kind of briefly dive into the creation of some of those images.
Yep.
And we'll maybe see if we can find some other interesting surprises in there as well.
All right. You ready to roll the tape?
All right, let's go.
Okay. I feel like I should do a countdown or something, but here it goes.
So, a lot of people don't realize that those gorgeous pictures that we see from the Hubble Space Telescope that we see here, those swirling rainbow nebulas and galaxies, they look so pretty, when it's your wallpaper on your desktop or your phone. But they don't actually look like that necessarily. So when I say that, of course, that's even separate from the fact that we're looking at them as a snapshot of time in the past, right? So the time it takes light to reach us here on Earth, that star might have burnt out or, gone supernova. And again, those images are really just tiny images of the past, depending on how far away it is. But this is actually also the case with color as well. So Hubble's cameras do record light, just like traditional photography, but it actually produces images in black and white. So it measures the brightness of the light that's reflecting off of things, but through a few different filters. And most commonly, those are red, green, and blue. And then we layer them and combine them and then colorize them to see that fuller range of color. Kind of like how, if you've ever looked closely at a TV or a computer screen, we've got those tiny red, green, and blue lights that combine to make more colors. So Hubble primarily is looking at colors that we can see on the visible spectrum, Roy G. Biv, with a bit of ultraviolet and infrared. But in contrast, the new James Webb Telescope is going to be taking photographs primarily in infrared. And that was decided because of discoveries made by Hubble, largely that the more distant objects that we want to look at are more highly redshifted. So their light is pushed more into that infrared spectrum. Now, that actually allows us to see stars and planets a lot better. Those that are, kind of just forming, but might still be hidden behind those big cocoons of dust, those nebulas. And they have a tendency to absorb visible light. But the infrared light in those regions can cut through the dust to show us what's inside. And this is actually a really great image here to talk about that. In these two pictures, you can see two colorized examples of the same thing. This is called the Monkey Head Nebula. This is a star-forming region. And on the left, we've got a colorized version of the visible spectrum. So you really see those dark clouds and the dust. But on the right, we've got a colorized version of the infrared spectrum. So many more and brighter things to look at here. So really great contrast there. But, another big difference between Webb and Hubble is going to be the size. So James Webb will have a much, much bigger mirror than Hubble. It's going to be over 6 times the size, in fact, which means it can look much further back in time. And as a result, it's also going to have a much better resolution. And it's also just larger in general. So Webb has a massive 70-foot sun shield, all right, that's about the size of a tennis court or about half the size of a 737 aircraft, they say. And it's got these 5 layers of aluminum-coated Kapton that are going to help to protect those infrared cameras even more from the rays of the sun because they have to operate at very, very cold temperatures. Now, in addition to all of that, it's also going to be placed much further away from Earth, too. So it's not going to be just outside of the blur of our atmosphere like Hubble is. It's going to be even further than the moon or any distance that a human, of course, has even traveled at something that is called the second Lagrange point. So in a nutshell, a Lagrange point is basically a position in space where objects kind of tend to stay put. And Lagrange point 2, which is 1.5 million kilometers directly behind Earth, is really great for astronomy because it doesn't orbit the Earth, which means not going to have any blocked views or temperature fluctuations. And at the same time, again, it's shielded from the direct rays of the sun. It's also close enough for us to be able to communicate with it. And it provides a really nice, clear, open view of deep space. So let's talk about some of these types of photographs that we'll be seeing, as well as, some that have been taken by Hubble in the past. If you are a longtime fan of Virtual Astronomy Live, you might recall that a while ago, in one of our past shows, somebody spoke about how colorful images that we have of space, of course, have later been colorized by scientists with different exposures to help us visualize how it might look, or to instead highlight some special features that we might not normally see with the naked eye. So for instance, this picture here, ESO 510G13, this is an image of a galaxy. The filters were used to simulate its actual colors. So what it might look like in theory if we were right up next to it. And the mostly white area in the center is where a lot of those differently colored stars are overlapping. So if you're familiar with light color theory, all those colors blend together to create white. But in contrast, if you look at this photo of the Cat's Eye Nebula, a dying star, this was created as a composite from 3 images that represented light wavelengths from either hydrogen, oxygen, or nitrogen. Now, in reality, those 3 wavelengths actually kind of only correspond to a limited shades, a lot of red, actually. So rather than making it look just like a big red blob, they decided to enhance the color differences. They used red and green and blue to make the structure of it a lot more apparent and also just prettier. So in this particular image, the light of the hydrogen is red, the oxygen is blue, and the nitrogen is green. So this helps us to see the structure more clearly, But remember, this is not necessarily what it would actually look like if you were to go to the Cat's Eye Nebula. Now, here's another image, though, of the same nebula, but in this one, you can see much more clearly the rings around it. So scientists think that there are at least 11 expanding spheres of gas caused by pulses of matter that are shot out from the central star there after it died. They think it happens about every 1,500 years, maybe due to magnetic activity. But they actually say that they think the amount of matter that's shot out with each pulse weighs more than all of the planets in our solar system combined. So you can actually see, using these different images, it gives us different ways of looking at things, even looking at the same thing, whether it be their chemical composition or learning about movement and shape. And hey, what better time to be talking about nebulas like the Cat's Eye Nebula than fall around Halloween, right? So in the spirit of the season, let's take a look at some other spooky sightings out there in the universe. Now, I do love to point out every year that Halloween is actually an astronomical holiday. It is one of our cross-quarter days, and that has to do with the transition of the seasons. And to the Celts of ancient Ireland and Scotland and Wales, Halloween was called Samhain, which means summer's end. But also fittingly, they also knew when to celebrate it by looking up for a small grouping of stars called the Pleiades. And that is near the constellation of Orion the Hunter in the night sky. We can still see it there now. If you follow Orion's belt, those three big stars, and you follow that out, extending out there, you'll find a tiny cluster of stars in Taurus. That's the Pleiades. And it was said that the Celts knew to celebrate Samhain on the night that the Pleiades climbed to the highest point in the sky at midnight. Now, today, it actually doesn't reach that point until November 21st. That's because, of course, the Earth wobbles a bit over the course of thousands of years. But their stories always associated the Pleiades cluster with sorrow and mourning because the clouds around it kind of look like teardrops in the sky. But, if you look more closely at it, you'll realize that is a cluster of over 1,000 stars. And they shine a bright blue because they are extremely hot. They are about 23,000 degrees Fahrenheit. That's over twice the temperature of the surface of the sun. And this is a really intense region of star formation. And all that dust surrounding those stars forms something called a reflection nebula because it reflects the blue light of the young stars. Now, right nearby the Pleiades, there is also kind of another eerie object, all right? It is right by the star Rigel in Orion, another blue star in our galaxy. Now, this region has a nebula of gas and dust that in particular tends to remind people of a character that we now associate with Halloween. So anyone out there have any guesses? What shape do you see in this cloud here? Tell me, let me know. And, what do you think it looks like? So again, something kind of Halloween-y, maybe a side profile of something. Am I going the right way? So if you look closely there, it kind of looks like a witch head, right? This is the Witch Head Nebula because it looks like a witch's head, right? You can see her eye, her nose, her lips, her pointy chin, maybe a big wart on the chin, and that big pointed hat, right? So this is also a reflection nebula because it reflects the blue starlight back to Earth. We see it shine blue, but it's not only because of the star's blue color. So this nebula also has dust grains in it that happen to reflect blue light a little more efficiently than red light. Kind of like how our daytime sky looks blue because the molecules in the atmosphere scatter blue light really well. But of course, if we really want to get into the Halloween spirit, everyone, you could always look at the infrared recolorized version and give her that classic green skin of the Wicked Witch of the West. Isn't that so cool? Now, in the constellation of King Cepheus, there is also another eerie nebula. What do you think this one looks like, everyone? Look closely there. Also kind of a spooky sight. This one is actually also so big that it spans over 2 light years across. So that means it takes 2 years for the light to travel from one side of it all the way to the other side. This one is called the Ghost Nebula, and it's called this because it kind of looks like ghosts rising out of the clouds of gas, right? Haunting nearby space. In it, you can kind of even see some arms reaching out, like poor trapped souls in there on the left. So this nebula is lit by new stars that are just starting to take shape and might form their own new clusters of stars, kind of like the Pleiades someday. And it's the effects of this star formation that really give the Ghost Nebula its shape, which is actually very appropriate because nebula are actually ghostly remnants of dying stars. They are these expanding gas and dust shells that have these enormous billowing rings, and they are effectively celestial ghosts. But there's even more spooky nebula in space. Some, though, we can't even observe from here in the Northern Hemisphere, like this one. What's that look like to you? This one, everyone, is actually called the Black Widow Nebula. So you see that spider in there. In the middle region of that spider's body, there are these yellow specks, and those are baby stars. So during formation, the stars give off these solar winds. There's these streams of charged particles that blow the surrounding gas outward, and it forms bubbles and cavities. So there were two really big cavities that were formed on either side of the new stars that give the nebula this, spider-like shape in the legs, which I think is so cool. Now, this one actually can only be seen from the southern hemisphere, below the equator in places like South America and Australia, which is maybe appropriate because, there are some super terrifying spiders that can kill you down there. But this one in particular is in the constellation Cercinus, which is the Mariner's Compass, which is also actually a constellation that you can only see down there because of its location. But it's not just cloud nebula out there too that give us some really haunting depictions in space. When astronomers look into the unknown, they don't typically expect to see something looking back at them, but that's what they saw with this next one. So this is a Hubble image taken in 2019. You can see this uncanny pair of glowing eyes kind of glaring in our direction. And those eyes are the most prominent feature of what kind of, to me anyway, looks kind of like a face, right? Or a skeleton or a creature. But this is actually an image of two distant galaxies colliding about 704 million light years away. This is called ARP Major 2026-424. It's named for the combination of the two astronomers who discovered it. But again, each eye is the bright core of a whole galaxy. So one of them has slammed into the other. The outline of the face is a ring of young blue stars, and other clumps of the new stars also form things like the nose and the mouth there. Now, the head-on collision helps to give galaxies that ring structure for about 100 million years, which is pretty rare cosmic circumstance, but it's due to their orientations. And although galaxy collisions are pretty common, most are not head-on like this one. So this is a rare treat. And then eventually in about 1 or 2 billion years, the two galaxies will fully merge into one giant one. But here is another fun fact, everyone. Scientists expect our galaxy, the Milky Way, to collide with our closest neighboring galaxy, Andromeda, in about 4.5 billion years. Now, to give you some perspective, that is about the same age as Earth, so it's a pretty long time to wait for it, and that would be pretty disastrous for all of us for a number of reasons, gravitational pull and collisions, you name it. But if you do happen to live long enough to see it, and it certainly would be spectacular, to see that galaxy coming closer, in the night sky to us, I wouldn't be too worried about it because it's likely that the sun will probably destroy the Earth first. So they say every billion years, the sun, which is of course our closest neighboring star, a dwarf star, gets 10% brighter as it starts to burn and use up its hydrogen reserves. And with that, of course, with that brightness comes heat. So you figure, all right, 40% brighter, that's definitely going to kill off the plant life. It's going to boil away the oceans. It's going to melt the ice caps and also strip pretty much all the moisture from our atmosphere, leaving us to maybe look something like Venus. And then Mars actually will be in the habitable zone pretty squarely. But at about 4 to 5 billion years is when they also expect it to switch to burning off its helium and to start expanding as a red giant. So that'll effectively vaporize Mercury, Venus, and Earth and anything left on it and in its wake, and then spread pretty much all the way to Mars in our solar system and turn into its own little nebula, a nebula within not the Milky Way galaxy anymore, but that new combined one. So you name it, Milkdromeda, Andromeda, I don't know. Now, on that note, you could probably guess what this image is, but what does it look like to you? Use your imagination here. So in 2014, NASA Solar Dynamics Observatory captured this ultraviolet image of our very own sun. It shows active regions as brighter because those regions give off more light and more energy. And they are markers of an intense and really complicated set of magnetic fields that are hovering in the sun's atmosphere called the corona. So this particular composite image blends together two sets of extreme ultraviolet wavelengths taken by the Hubble Space Telescope. They are typically colorized in gold and yellow. And it really does create, I see it in the chat, someone says, a spooky kind of jack-o'-lantern effect or a spooky face, right? Just in time for Halloween. So who knows what kind of beliefs and stories the Celts might have had if they had, seen all of these extraordinary things that we can see in space today. But one thing is for sure, the launch of the James Webb Telescope is going to let us see even more cool images just like these, but even further into space, even further distant nebulae and galaxies, and really give us more answers about the origins of our universe. Maybe we'll find a few tricks of the eye like we just looked at today, but there'll definitely be a ton more treats for scientists and astronomers around the world. So really fun stuff to find in space.
I know. So when we do the pre-show like that, Elysia can see me. She can see my camera, even though y'all can't see the camera. And I'm sitting there looking at her like this every time she does a pun, like.
I guess that's kind of become my thing, huh?
It is kind of your thing. It's really cool. It's interesting that when, as far as we could see out into the stars, was the stars themselves, we made constellations, right? And we sort of imagined drawing these pictures in the skies, and then once we were able to see even further because we made rocks smarter or whatever it is we did, figured out how to make telescopes and technology and all that sort of stuff, we continued to try and sort of put shapes and stuff like that around it. So even though our technology may have advanced, our imagination is still kicking, right?
That's right. That's right. And so I'm so excited to see when these new returns come in, hopefully, I guess, summer of next year. What other kind of fun things? It's so much fun to see these new images as they get released and to kind of let your mind wander and sort of imagine what kinds of shapes and things might be out there.
Absolutely. Just it's amazing that when you sort of look up, it just keeps going, right? You look up and you can see some stars, and then somebody zooms in a little bit and it's like, oh, there's some planets, and you zoom in some more and there's like more stars, then you zoom in some more and there's gas and dust and stuff that you can't see with the naked eye that you can see. The more and more you zoom in, the more detail there is. It's one of the coolest things about looking out to deep space, I think,
And what's even cooler too, like I was saying with the infrared stuff, now that James Webb is going to primarily be looking at that, we're going to see things in new ways that we have never experienced before. Hubble primarily does the visible spectrum. So that's, again, the Roy G. Biv, what we can see with a little of ultraviolet and a little infrared. That's going to mainly be shifted out there. And we are going to see so much deeper into the universe and into the past, really, the origins of the universe with this new technology. It's incredible. It's going to be so exciting.
Absolutely. Well, y'all, as we always do, it's always a good time. You may think like, oh, the pre-show, like people are walking in or whatever. Maybe you only caught half of it. It's okay if you only caught half. If you got a notification or something like that, and then you ended up over here and you were halfway through Elysia's presentation, you can actually go back after the fact. The VODs are always available, so if you missed a little bit of it, all of these are going to be listed on all the different channels, I guess, if you want to get caught up. So we'll see if we can't put a link into chat with some instructions on how you can get back to that. But Elysia, as always, it's always a good time to be able to hang out and see what cool presentation you've come up with for us this month.
Always a pleasure, Doss. I'm so glad to be back. So much fun. And everyone, have a fabulous Astronomy Live.
So I say this month, right? It's not just this month. You do
it's
presentations constantly. Like
I'm always here.
Twitch.tv Intrepid Museum, on the Intrepid YouTube, on the Intrepid Facebook, like all over the map. You do regular shows like this that people can come and just hang out. You can't make it to the museum in person, and you can catch Elysia here online from the comfort of your computer or couch or whatever, right?
That's right. Yeah, we do all sorts of streaming stuff. We've got Intrepid Adventures on Thursdays at 3 p.m. for the whole family, all sorts of topics, and all sorts of different events and things that we're always doing. We team up with partners all across the country, and we love, of course, doing this with you.
Yep, absolutely. Well, y'all, say a massive thanks to Elysia for hopping through here and talking with us about some of those deep space images as we got prepared for our James Webb Space Telescope here. Elysia, always a pleasure. Thank you so much.
All right. Thanks so much, everyone. Again, have a great Astronomy Live.
All right. We'll see you next time. So, folks, we are not done. That's just the pre-show there. And we still have our special guests from the James Webb Project itself who are going to come up here. I'm going to go AFK for just a minute, and we're going to have just a little spinning standby screen. I'm going to see if we can't get our special guests connected to the call here, and then we've got an hour and a half so that we can talk with them and learn about the James Webb Space Telescope. So, as always, give me just a minute here. Let's get them connected to the call and make sure everything's good to go. Don't go anywhere. We still have an hour and a half of the show here. We're also going to do a little bit of a Q&A at the end. So if you have questions about James Webb, maybe you want to know what flag the pirates were flying when they tried to take. Hey, we'll talk about the pirates that were supposedly after James Webb whenever we come back. But we will have a Q&A period at the end, all through the course of the show. If you have questions for us, you can put it into any of the chats or comments. I'm looking at everything. I've got like screens like Mission Control all around me here. And when I come back, we'll see if we have our special guests. Stand by for me, and thank you so much. Again, it's Intrepid Museum Virtual Astronomy Live this month, talking about James Webb. All right, folks. Let's see if it's worked here. We have all of our special guests on the line. I think I have everybody in the right slots and stuff. You know, all the names look like they match up. But here we are with some of our folks to talk to us today about James Webb Space Telescope. And I'm going to point out something really cool. In one of the cameras, the live cameras right this way, it's the actual James Webb Space Telescope. Like in the background. It's not a model. It's not a drawing. It is right there on the actual thing. So a little bit tough audio there because that is it's like a viewing room with the James Webb behind it. So help us deal with the audio here. Just please be understanding. But that right there is amazing. Let me introduce the folks who have joined us here today. You've seen her on our show before, our fantastic moderator, Summer Ash. Thank you so much, Summer, for joining us today. How are you doing?
I'm happy to be here. I'm excited. Repping my JWST gear.
All right. It's right there on your shirt, it looks like. Excellent. And are you ready to get going with introducing our special guests?
Oh, absolutely.
All right. Well, let's go ahead and get the show started, shall we?
Okay, great.
All right. Sounds good. Go ahead.
Hi, everybody. I'm going to welcome our special guests today. I am joined by Bill Ox. Actually, I didn't even know how to pronounce your last name, Bill. Is that correct?
Oaks? No, it isn't right. It's Bill Oaks.
Oaks. Thank you very much. Bill has 30 years of experience in the aerospace industry, and he's worked both in private industry and for NASA. He's currently the project manager for Webb for the James Webb Space Telescope. And he received a BS and MS in electrical engineering and a master's in operations research. And he began his career back in 1979 with Benedict's Guidance Systems Division in New Jersey as an electronic software engineer, developing the flight software for the Hubble Space Telescope safing system. So very cool. Also joining us today from Peru and in front of the actual James Webb Space Telescope, which just, you win hands down, is Dr. Begoña Vila. She's an instrument systems engineer for James Webb at Goddard Space Flight Center, normally in the stateside. And she supported Webb's cryogenic testing at Johnson Space Center in 2017. And she's continuing to support the testing for the observatory through launch at the end of this year, as well as commissioning the telescope after launch. She also actively engages in Spanish and English media interviews and outreach activities for the Webb program, including lots of science, technology, engineering, mathematics, STEM events. So welcome, Bill and Begonia. It's great to have you both today.
Thank you.
Thank you. It's great to be here.
I wanted to start with my favorite question, which is just kind of to ask each of you sort of how you got into science and engineering in the first place, and then how you wound up at NASA where you are today. So who wants to go first?
Begonia, you want to go first?
You want to go first?
Yeah. All right, I'll go first. So let's see, when I got out of school, when I got high school, I really did want to do engineering. That was what I wanted to do. So I got into electrical engineering. Went through 4 years of bachelor's and then got a job with Bendix Guidance Systems Division up in Teterboro, New Jersey. And we had a contract, we were subcontract to Lockheed Martin for building various components of the Hubble telescope. And I worked up there for about 4 years, stayed with them, but then I transferred down to Goddard Space Flight Center as a contractor to support the mission operations for Hubble. And I worked there through about 1990. And then one of the folks I knew from NASA asked me if I wanted to come work for NASA. Still supporting Hubble. And came on to NASA. I spent another 8-9 years supporting Hubble. I was told I was almost 19 years on Hubble. But I ran the operations at Goddard for the first 2 Hubble servicing missions. Then I left Hubble. I managed Earth science missions for about 13 years, 2 different ones. And then in 2010, I got asked to come manage JWST.
Fantastic. How about you, Begonia?
Well, I started in Spain, and that's where I did my degree, and I did my PhD in astrophysics in the United Kingdom. And then I came across the water, as they say, to Canada. And at that time, I left the university background and moved into private industry, working in space. And I was lucky to start on the James Webb in 2006 under the Canadian Space Agency, who is one of the contributors to the James Webb with 2 of the instruments. And then when we delivered the flight model to NASA, they asked me to come and join them, and I was thrilled to do that. And it continues to be an amazing journey.
I bet. Bill, I'm glad you brought up Hubble, because I think a lot of people are so familiar with Hubble, and sometimes they think of JWST as like the new Hubble or a replacement for Hubble. It is not exactly true. And so I think,
yeah, well, I get asked this question all the time. We are, we like to, they refer to us, and even we refer to ourselves as the follow on the Hubble. But that would imply we're looking at the same part of the light spectrum and so on. We really aren't. There's numerous differences, and obviously when you look at a model of Hubble, it's very obvious. But one, we are a lot bigger than Hubble. Our primary mirror is about 7 times the size of Hubble's primary mirror.
Gus, could you bring up the image there's an image that's JWST versus Hubble or something?
Yeah, just one second.
I think we're going to put that picture in,
Yeah, it's a great visual. Yeah. It's coming. Keep going, Bill.
Keep talking.
Okay. And the other part of it is when you take into account the advancements in our detectors that we fly in our science instruments, we are about 100 times more powerful than Hubble.
Yeah,
now,
there it is.
With looking at a different part of the light spectrum. The Hubble is primary visible. We are an infrared telescope. We have the gold coating on the telescope because gold is sensitive to the infrared. We do that because we wanted to be able to see back the very beginnings of the universe. And when you start looking back, as light travels through the universe, elongates and goes from the visible portion of the light spectrum, and then does a redshift and goes to the infrared portion of the light spectrum. Those are like the really big ones. Then you get into the fact that we're a cryogenic telescope. We've got a sun shield that's the size of a tennis court, and we can go on and on and on.
Yeah, Das, you want to like circle, do your magic marker circling like on the wavelength diagram? to sort of show where that infrared, those longer wavelengths for JWST are?
Sure, no problem. As long as I don't use a permanent marker to draw on my screen.
Please don't.
So
Yes.
you're looking down here where James Webb is an infrared and then Hubble is a little bit lower, or I guess higher frequency.
Correct.
Yeah, right.
Yeah, so you mentioned the gold. I really wanted to talk about the gold too, because you said that it's sensitive to infrared, but in what way do you mean? You meaning it just is helping capture those photons better?
Gold mirror is more sensitive to the infrared spectrum versus a normal silver-looking mirror.
How much gold is on there?
It's the equivalent of a couple of wedding bands. It is not much on the entire telescope.
Spread out, the whole thing.
Yep. Mm-hmm.
That's incredible. Wow. And those pieces, individual pieces, there's about 18 of those hexagons, right?
Right.
I saw that, I'm not sure who took these photos, but we have some, DOS, if you could bring them up, of the mirror assembly. They're like very beginning stages of putting the mirrors together.
Yeah, so the way the telescope came together, Goddard was the home center. We subcontracted out to Northrop Grumman for the observatory. Goddard was responsible for the instruments and bringing the instruments in here and integrating them into a package. Northrop subcontracted the Ball Aerospace that had responsibility of the optics. But they were all delivered to Goddard, and Goddard did the assembly here. So I'm trying to see the pictures you have up there. If you have the first picture I sent you guys, that's how we actually put the mirror, each individual mirror segment, onto the back plane of the telescope. So we used a robotic arm to bring the segment down, and then you can see the technicians there inspecting it, and then they worked from underneath to basically fasten that mirror to the telescope. And if you go to the second picture, number 2, I had sent you guys.
Yeah, that one.
Yeah, so when we put the mirrors on, they had covers on them. Then we had to take the covers off. So we had folks, and then you can see in this picture, a couple people on diving boards out over the telescope, gently lifting those covers off and then taking them off to the side. Pretty nerve-wracking to watch. We actually, we have a big viewing mirror into our clean room at Goddard also, like where Begonia is. We actually pulled the curtains that day for a few days because we didn't want the technicians being distracted at all by anything that was going on, because you didn't want to have an oops and it fall.
That's fair. I bet that's very nerve-wracking for those two people right there.
Yeah, it's also nerve-wracking for the project manager to be watching it too.
Fair enough. Yeah, Begonia, when you were at Goddard, how often did you guys go down and just spend your lunch hour just checking out the telescope?
Yeah, it was pretty cool to be there. The instruments arrived first and they were put together so we could do the testing on the cryo chamber that we have at Goddard. As Bill was saying, it's an infrared telescope, so you have to make it cold because everything emits at normal temperatures. And also James Webb is going to be very cold once it's in a space very close to absolute zero. So we have this chamber. And then in parallel with that super cool testing that we were doing, they brought the mirrors and we could see them exactly what Bill said, putting them together until finally we were able to have this awesome set of mirrors, and we were all, pictures and looking at them. It was very special.
So you mentioned the cryogenic testing. So when you're testing the instruments, I know you want to cool them so that any of the heat from the electronics doesn't actually turn into a signal for the telescope, right? But how much do you have to cool them once they are actually in space and in deep space?
Yes, so they are going to be very cold. They are going to be 40 degrees above absolute zero, 40 degrees Kelvin. In Fahrenheit, it's around minus 385 Fahrenheit. So you can think a lot of things. When you build something, when you put something in the freezer, it changes. Its properties change. So the same happens when you build a telescope. We cannot build it at those temperatures. We build it at ambient temperatures. And we know once it gets cold, it's going to move a little bit. So you kind of have to build it at ambient, knowing it's going to get here when it's cold. But then to make sure you have done it correctly, you have to go cold. You have to full vacuum, go that cold, and operate everything and check all the alignment. Is the light arriving where you need it to be? Are all the commands that you're sending to the instruments behaving as they should? So that's certainly a key part of the James Webb. And James Webb is so cold that the chambers we had to use, we used the one at Goddard. And then once those mirrors were together, we needed a bigger chamber. And I'm sure Bill is going to mention this. We had to go to Houston, which has the chamber that was used for the Apollo missions. So every time you are running that test, you are checking that everything works. You have to be very careful and run all the operations as you will do when you are on flight. And it's one of the tests we have to do to make sure everything works and is aligned properly.
Yeah, Bill, where is the test chamber in Houston? And how big is it if it was used for Apollo?
Yeah, it's at Johnson Space Center. I don't remember the exact size. It's been so long ago now, the exact size of the chamber. There's a picture. If you pull up picture number, where'd it go? Picture number 6. It shows there's JWST going into the door of the chamber. This chamber, as Begonia mentioned, was built for the Apollo era for testing the capsule and the command module integrated together. We took that chamber and converted it into the world's largest cryogenic chamber, which was a project within itself.
I bet.
We went down there for the testing, and this is the test, and Begonia pointed out some of it, but really this is the test where we were able to prove that we have a telescope that did not have the same issues that Hubble had when it launched. So we already know we can focus the telescope. So that's all great. The other point that Begonia didn't mention, and she can give you firsthand experience, is in the middle of this 100+ day test that we were running down there, Hurricane Harvey hit in Houston. And we had to have folks stay with cots at Johnson. We told the folks to stay at the hotel. Folks brought in food. We suspended testing for a couple of days just to keep everything safe, because people were going to be working long hours and getting tired. We didn't want any mistakes to happen. But one of the things I'm very proud about with the team is that when Harvey cleared and we got back to a normal schedule again, our folks went out into the community and helped volunteering, cleaning up the community, which I thought was great. But Begonia can add about firsthand experience of being down there during Hurricane Harvey.
Yeah, it was a really cool experience, as Bill says, because of being there, because of doing the testing, and then for seeing firsthand, the community and how difficult it was, and being able to help a little bit. I think James Webb has had this kind of adventures when we are doing the cryo testing. When you are that cold, you have to be very careful that you don't lose power and that anything happens that will start a warm up of the chamber that you cannot control, because it's such a delicate process. So we watched for Harvey when we were in Houston, and when we were testing at Goddard, we had a snowstorm, which was, we could predict it a little bit better, but we stayed at Goddard for a weekend, and we borrowed the offices of colleagues, and we put mattresses, and we brought food in. So certainly we have had lots of interesting experience along the way when testing James Webb.
Yeah, a lot of science sleepovers.
Yes, exactly. and maybe something else that maybe we can mention is the other thing that Johnson, the test and Johnson allowed us to do was to check that we can align those mirrors. I think as you know, right, we want a bigger mirror, is a bigger bucket, it collects more light. So it lets us see things that are fainter. But it didn't fit in one piece inside the rocket, the Ariane rocket. So that's why it's made of those 18 smaller mirrors that we can fold. But then when you think about it, when you open those mirrors on orbit, and I'm sure we will talk about that, and we look at the star and you take a picture, you are going to see 18 stars, because each mirror is doing its own thing. So there is a very complicated process that's needed to align those mirrors on orbit. So you end up with a really nice mirror where you don't notice there were 18 there before. And the testing at Johnson allowed us to confirm we could do that and that we are ready to do it once we are on orbit.
That's amazing. I didn't know that about the individual ones. But how many have you on Earth? Has it been folded and unfolded under its own power ever?
Yeah, we've done the testing about 4 times. You don't want, especially with the sun. The sun shield is the most complex of the deployments.
That was my next question. Have you?
So we can. I actually provided a little time lapse video that runs for. Well, it also has some what we call beauty shots at the end of it, but it does show the final deployment. We can run that, and then I saw back behind you. You had a picture of the whole telescope. I want to talk about that for a second too. But if you run that video.
This one here, right?
Yeah.
All right.
That gives you great scale too with all the little people.
So this shows shows the entire deployment of the sun shield on the ground. It was the final time we deployed it, which was very successful.
And is it being
maybe
under? Okay, go ahead.
No, something that Bill is going to mention is, again, the sun shield is meant to be deployed in a space where there is zero gravity, but we have to test it here. So there is a lot of support equipment, a lot of, the team has to do a lot of work to make sure you show it can be deployed, but it's not seeing the weight of the gravity, so it doesn't get damaged. Right. And I'm sure Bill knows all about this as well.
Yeah, no, that's more, you can see some of it in the video. So it's a deployment, but we have a lot of ground support equipment to compensate for gravity and offload it for the effects of gravity.
That's a great point, and that changes like the friction too, probably between the layers.
Right, and that's a challenge that every spacecraft has if it has a deployable, whether it's a solar array. But we have approximately 50 deployments, and I throw some other numbers out there while you're watching that beauty video. We have 178 release devices encompassing about 9 different designs. We have 155 motors. If you look at the sun shield, there's about 600 police assemblies. There's about 1,300 feet of cable associated with the deployments. Out of those 178, 107 of those devices are associated with the sun shield. So you can kind of get the idea of the complexity that we have to deal with when we deploy JWST. I always say things pop up, unroll, pull out, you name it. This telescope will do it.
It does it.
So it's pretty amazing to work on and watch all this come together. And we do all of this. I think Begonia may have some stuff in our on-orbit commissioning. But we do all those deployments in about the first 2.5 weeks of the mission. I like to call this we have 2.5 weeks of high anxiety.
I was going to say it's kind of like holding your breath, which is what the guys did on the moon landing, but they only had a couple seconds to do that. Whereas you guys
the Mars folks, they have the 7 minutes of terror. We have 2.5 weeks of high anxiety.
Yeah, what is that time?
Whilst the telescope is moving, right, that is doing all those deployments, but it's on its way to where it needs to be. So it's certainly, yeah.
Yeah, Begonia, what does that timeline look like from launch?
Right, so
after launch.
It's going to take about 6 months to have James Webb completely ready. And as Bill mentioned, I think we are all a bit more anxious about those first 15 days. That first month is where all the deployments are going to happen. So you're going to see the sun shield, the solar array that we need, the antenna to talk to the ground, the mirrors, eventually are going to open and come down. And then after that, we take about 2 months to do that process that we mentioned. Everything is deployed. We take an image and we have the 18 stars. So we are going to take a process using some of the instruments to make sure the mirrors are fully aligned. And then we have the final period of commissioning when everything looks really good, and then each of the instruments is going to start taking the first images, the first spectra, and being calibrated, make sure they have everything that they need to be used for science. So all of that, it's about 6 months. As Bill knows, we know what we are doing minute by minute of that time, what should happen. And we have done many rehearsals to make sure we know we are ready and what goes when and what needs to happen when, et cetera, et cetera.
Yeah, how long will it take to get from launch orbit to the final point of the Lagrange point, L2 on the far side of the moon?
About 29 days. We're pretty much booking it, and we pass the moon in about a little over 2 days, maybe 2.5 days. We go right past the moon, and it's when we get past the moon is when we start our major deployments. Our first deployment obviously is our solar array panel. That's within the first hour after launch. The good part, we only have really 2 time critical things, so it's not like we're rushed for time. And that's the solar array deployment and our course correction maneuver that's done at the end, towards the end of the first day after launch. Everything else, if we have an issue, we can stop, pause, and figure out what's going on. We've developed, I'm an old operations guy. We developed a toolbox of procedures to help us with on-orbit issues. And we've got over 340 procedures that we've developed in case something happens on orbit. They can be simple things like, try sending that command again, go to a redundant side of an electronics box. There's something more complicated where maybe part of the sun shield didn't quite deploy. We actually have algorithms where we can kind of shake the observatory at various frequencies. We call it the shimmy. And then we can actually spin it, which we call the twirl, and we can spin it in either direction to try to shake something loose if it's stuck.
Yeah, I can't imagine the complexity of the contingency planning that you guys have to do.
It's been going on for a few years, and folks sit down, they try to think of what can go wrong, and then when you get them all together, you say, okay, well, these are not reasonable. These are, this takes 3 failures to get here. We're not. So then you start moving down that list to something that's manageable. But I think when I did a lot of this for the Hubble first servicing mission, one of the things that's really valuable that comes out of it, it gets you thinking, your mindset on what do I do when something happens? Because odds are we'll do all this planning and something's going to happen and it's going to be something we didn't think of. And then we're going to have to go back in and tackle that problem.
Have either of you gotten to spend time inside the clean room with the telescope?
They don't let managers do the hardware.
Yes, I was going to say they don't let. No, Bill has been in the clean room, but for special moments, which is special. And even myself, I have been in the clean room normally to do an inspection. Everything is done, and they want you to come and see. I think the people that are in the clean room are specialized people as well, right? That they know what they're doing with the hardware or with the electronics. And you don't want, you only want people that are properly trained near the telescope, and we have all the functions that we have to do. But it's always special when we are allowed to go in and look at some of it, for sure. I'm sure, Bill, you feel the same, right?
Oh, it's very cool. Last time I was in there we're in October, not quite a year ago, when we had just completed the final deployment of the sun shield, and myself and Scott, who's my counterpart out at North Carolina, the project manager up there, we went in and got to look around, and they did some photo ops with us in front of it. So it's a very cool experience.
Yeah, I would imagine it's very special to be in the presence of it without a glass, in your way.
And also because now you're standing on the floor and you're looking up at it, and you really get a sense of the size, and you sit there and think, what did I get myself into?
And then it is very cool, of course, to wear the bunny suits, right? And I think everybody listening knows, right? We try to keep the telescope and everything as clean as possible before we launch. That's why it's in that special clean room. And we always say we humans are one of the dirtiest things you can put in there, right? We have hair, we have oil. So it's just getting dressed to get into the clean room is an experience in itself. So
I can imagine. Now, when we saw the whole time lapse of it unfolding, you see the top of the sun shield, which looks a lot more sort of silver, but when it's all folded up, it has this pinkish hue.
It's like a silicone coating on the bottom. The sun shield is actually very amazing. Since we are a cryogenic telescope, we have to keep the telescope very, very cold.
Right.
So we basically do it, except for one instrument detector, we do it passively with that 5 layers of that sun shield. Each layer is thinner than the thickness of a human hair. It's pretty amazing. I got, when we were building the prototypes, it was built by sun shield was built by a company down in Huntsville, Alabama called Nexol. I got to go down and look at it. I went in their clean room, and they said I was walking underneath it, and they said you need to slow down because just the motion of your body and how it disturbs the air was causing that sun shield to move. But from a thermal standpoint, so the business end of the telescope, the back end of it, where the electronics are and communications, the solar array, that faces towards the Earth and the sun. So that sits at about plus 185 degrees Fahrenheit. By the time you get to the side, the cold side, you're sitting at minus 485 degrees Fahrenheit. So you have almost or over a 600 degree difference just from that sun shield being there. So it's pretty amazing.
Yeah. Is that kind of like being on one side versus the other of Mercury? Although maybe not.
Being in the shadow and stepping out of a shadow. It might be a little bit bigger temperature difference, but the same type of idea.
Yeah. And so the sun shield, what's the risk at where you're going of micrometeorites and things like that?
We went through and did numerous studies early on about the impacts of micrometeorites. Now, in the sun shield itself and its construction, there are basically rip stops in there. So if you do get a hole and it starts to tear, it will stop. And we did enough analysis to give us full confidence that even with some micrometeorite hits, we're fine. We'll be fine. And it's the same thing with the mirrors, because the mirrors are exposed, unlike Hubble where it's buried. We did enough studies to understand that any micrometeorite hits on those mirrors, we're still fine. We can still meet all our requirements.
And so you were mentioning, I guess, this little box down here where some of the electronics and the solar power.
That's basically we call a spacecraft bus that was built in-house at Northrop Grumman.
Yeah, there it is.
They did a great job. Oh, I see the diagram up there. They did a great job with that, and they were responsible also with building the sun shield. They went out to various manufacturers like Nexol. Used to be a company called ATK that built the composite graphite backplane of the telescope and of the what we call the unitized pallets that hold the sun shield when it's folded up. They've been bought numerous times, and now Northrop Grumman owns them. So
yeah, I used to work for Orbital Sciences, I guess, at one point, and then they both got bought by Northrop.
Yep.
Yes.
It's as an international mission. I tell folks, over 20 years, we've had over 10,000 people work on this satellite. But we've had folks from over 14 countries throughout us, Canada, and throughout Europe. We have had folks from 29 different states in the U.S. work on this telescope. It really, truly is an international partnership of a very grand scale. And now we're down in South America, where Begonia is with the launch vehicle and getting, launching in less than 2 months.
Yeah, that's a perfect segue. I was going to say, and Begonia, you are now in French Guiana in Kourou, where James Webb will launch. So why is it launching from there and not from somewhere in the States?
Two reasons. One of them is the launch vehicle is an Ariane 5, which was one of the contributions from the European Space Agency. As Bill said, this is an international collaboration. And then the launch site is close to the equator, so it takes advantage of the centrifugal force of the Earth to help us escape the orbit a bit better. So this is where Ariane launches from, and this is where we came to launch James Webb. And I can mention Bill was here. He's not here now, but he was here last week because we had, as I mentioned before, we do some of these rehearsals to make sure we are ready to go. So we did a rehearsal for the day of launch, and follow all the steps as if we were going to launch. And it was very emotional just doing it. Even we did a lot for real. So, and I'm sure Bill, I mean, I felt emotional, so I am staged in a different area to monitor some of the telemetry. Bill he's in a cool area where he gives the go, no go with Ariane Space. So if it felt emotional for us, I just can't imagine how it felt for Bill being over there.
Not during the launch count, not during the rehearsal. It was more figuring out what to do and how not to screw up.
More for yours, yes. Yeah. And then, of course, we are here, so the instrument, it had to arrive, and I'm sure Bill has a lot of those pictures as well. And it had to be a stage, as you see it behind, and now it's connected electrically. So just now we are running these electrical tests that we have to do to make sure that the shipment went okay and that everything behaves as expected. And then once we have confirmed within the next few days that is the case, it can move through the next phases to being fueled and then move to the Ariane, et cetera, until launch day.
And you were there when it arrived. In Peru, correct, Begonia?
Yes, I was very lucky. I was yes, these things that happen. So I was there. The boat arrived, and by chance, the hotel where I was staying, it was going through that area. So it was an awesome sight to see the boat, knowing James Webb was there. And then, it got staged by the transportation team, etc. And then we got to see him. The telescope arrive and see him behind me as you see. So super special times, I think, for all of us on the project.
It was we were out, both Begonia and I were out west when it left Northrop Grumman, and that was very emotional. I actually gave you guys I have a whole series of pictures we can just flip through that.
I was going to say, if Joss could bring up 11, because I think that one's really great, showing the size.
Actually, can you bring up 10 first? I'd like to just talk about 10 for a minute.
No problem. They're your photos. Go for it.
Okay, so 10 shows us being lifted and going into the shipping container. What you're watching there is a 14,000-pound observatory being lifted and then lowered onto a fixture that will then tip it horizontal to get it into that shipping container. And then if you start going on to was it number 11?
Yeah, I like that.
That's where we're starting to lower the cover over the top of the telescope, and then just go right down 12 through 16. That's the truck as we're leaving Northrop Grumman. That truck, actually, you'll see a picture in a sec, went actually on the ship. We brought the truck driver down. He's the same truck driver who's been doing our transportation for I don't know how many years. We brought him down to French Guiana to drive off the ship. That's a picture of our shipping container with the truck right next to our ship. That is backing onto the ship, which was a really cool experience to watch because you have to actually go onto a barge that's perpendicular to the ship. A tug makes it then parallel to the dock. It brings it up to the ship, and a garage door comes down. It was amazing how they can control that barge. That's a picture of us showing up down in Peru. And there we are coming off the ship.
What an amazing trip. So I think it took about 16 days. Is that right?
Yeah. And we had 4 or 5 folks on the boat to monitor the environmental control systems. No one got seasick. They said it was a French ship. It's the same ones that ESA use. They have two sister ships. And this one, the crews are both French. They provided a French cook. So when I saw one of the guys down in French Guiana, I said, "Hey, anybody get seasick?" No. So we all gained a few pounds because the food was so good.
I can imagine. So was that the chamber that it's in, climate controlled and vibration controlled or something like that?
Oh, it's all it's all climate controlled, and we pump dry air through it, and to keep it the humidity down and so forth. We had requirements for sea states, and we identified safe ports of call all along the route. So if we started seeing sea states greater than 5, I think a sea state 5 is like a 16-foot wave. We could actually go into a safe port of call. We had one instance coming out of the canal. We thought we were going to see that. We were going to actually anchor for a couple of days outside of the canal, because that's one of the safer things to do. But 24 hours later, the forecast changed and we were able to keep going. We also had it outfitted with accelerometers, so we knew what type of environment from whether you might call it vibration type environment, mechanical type environment that it saw. Downloaded that data, so we knew it had a very smooth ride going down to French Guiana.
Yeah, I'm kind of jealous of the telescope because it got to go 16 days at sea through the Panama Canal.
Yeah, except they went through the Panama Canal. It started at dusk, so they went through it during the night, so we really didn't get a chance to see anything.
That makes me feel better. So you mentioned the accelerometers and vibrations. So that was, I would imagine the whole assembly also had to go through some vibration tests.
Yeah, we have a picture. Where did I put that? It's number 7. So the most violent environment that we see is during the rocket ride.
Yeah.
So we did testing at both component levels. For example, the integrated telescope and instruments went through a vibration and acoustics testing, as well as the integrated spacecraft bus and sunshield. This is the entire observatory. So the vibration test basically emulates the vibration environment it sees inside the rocket fairing during the ride. It also goes through an acoustics test that simulates the acoustic environment inside the fairing during the rocket ride. And we got through all those, and that was all part of this. That was actually last fall that we went through that environmental testing. And then that video we showed earlier, the final deployment, that occurred after this final set of environmental testing to prove that we could still deploy after the rocket ride.
Right.
I'm trying to draw vibrations on there, by the way. This is actually like the vibration table, right?
Yeah, they're not doing. You can see guys working on it, so they're not doing any vibration at that point.
I just had to improvise there.
How soon before the actual launch will the telescope be put into the fairing?
Early December. Early December, we make to the launch vehicle. Fairing encapsulation occurs. I'm trying to remember the schedule off the top of my head. We launched the 18th, a week and a half or so before that. So it's pretty exciting times. A lot of electrical checkouts that are going on. I mean, we have the big electrical tests now, but there's more when we get onto the fairing. Onto the rocket and so on. And at the same time, they're checking the rocket out. And last week, when I was down in French Guiana on Friday, we got a tour of some of the facilities. And the facility where you integrate your satellite or satellites onto the rocket, we were in that facility, and the Ariane 5 that launches this Friday evening was in there. And they were just integrating the second. They have 2 satellites on that one. And they were integrating the second satellite.
So Begonia, we talked a little bit about the science and infrared wavelengths that James Webb is mostly going to take advantage of. But I know that you sort of sent ahead some images or talking about the science that the instruments will do. So how many different instruments are there on the telescope, and where are they with respect to sort of the mirrors and the sunshade?
Yes, very, very good question. So there are 4 instruments that are dedicated to science. 2 of them are contributions from the European Space Agency. One of them is the US. And then one of them comes from the Canadian Space Agency. And then there is an extra instrument, which is the guider, which allows the telescope, the observatory, to keep the pointing accuracy that is needed to take the images so they don't move, and the spectra. And that's also a contribution from the Canadian Space Agency. And I think if you saw the picture before, the instruments are mounted together in a box that's behind the mirrors. So people can see, you see the mirrors, and just behind are where the instruments are. So the light, it hits the big mirrors, then it hits that little mirror that you can see standing out, and that mirror then reflects it to the black spot that's in the center of all the mirrors, and that's where the tertiary mirror is. and the instruments then are behind there, and each of them collect all the light. I think James Webb was designed with important goals for science, and Bill mentioned some of them, right? We want to look back in time and see those first galaxies that were formed, those first stars that were formed. We know how our galaxy looks like, and we live in one of the arms of the galaxy, but we already have pictures looking back, knowing that the initial galaxies didn't look like that, so they were born in a different way and changed to become the galaxies that we have. James Webb is also looking at those first stars that were formed and the planets around them. And then moving that forward is going to help us answer a little bit this question about if we are alone in the universe, right? We are going to, now we know there are planets around other stars. We know now there are hundreds of them. So James Webb is able to look into the atmosphere of those planets, and of course what we're looking for is signs of life, right? Do they have water, carbon dioxide, methane, something that we will say life could be there, like we know it here on Earth. So a lot of super interesting science themes, and we say James Webb is going to change the astronomy books, because it will teach us so many new things. So. And I think we had a picture about the wavelength, right, which Bill had already mentioned, right? The light is traveling, so it moves to the infrared. So we need to take the pictures on the infrared. But then the other thing that the infrared does is stars and planets are born in parts of the sky where there is dust and gas. So with our eyes, with the visible, we know they are there, but we cannot see them. But the infrared looks behind that, you can see it. And I think there was a picture that is the same, exactly, thank you.
Just put it up.
It's the same part of the sky, it's the same part of the sky. We know there are stars there, and in one of them we just have to infer that they are there. When we look at it on the infrared, we can see them, we know they are there. So James Webb has a lot of very cool capabilities for science, for the science that it was designed to do.
You might not be able to answer this, but has there already been a first light target chosen for what it's going to image first?
We don't know. They have not. All I know is they have not made that decision yet. If you anybody follows JWST, last year they announced the early release observations, the EROs. It will be part of that group. I think there were 15 or 16 proposals chosen for that. That'll be all actually the first science that you get a chance to see, and it's everything from planetary to looking back in time at the early stars and galaxies and so on. But they have not chosen yet, and they won't tell us even when they do choose.
I didn't realize that was a proposal process, though.
For the early release observations, yeah, that was a proposal process that was out there. And then earlier this year, we announced, Space Telescope Science Institute, where we do the operations for the telescope, announced the cycle 1, which is the first year's worth of observations and the proposals that were selected.
I'd be curious to know how many applications they get.
We were, for the first year, it was 4 times that were prescribed.
Makes sense.
Yeah.
So what has been your favorite moment working on JWST so far?
Oh, for me, there's too many of them. And everybody will say, oh, launch, but launch is just the beginning, right? It's the rocket, not to downplay the rocket, but it's the truck that gets us up to orbit. I think when we get to where we are fully deployed, there's a lot of us who are going to go out and have a drink that night. And when you see those first science images coming out and you know it's working and everything, I think that'll be another moment. But there's been so many over the almost 11 years I've been on this program. And this program is made up of a lot of really special people. I tell folks this is the best job I've ever had at NASA, and I enjoy working with all of them. So it's across both, not just NASA, but Northrop Grumman and all our other partners, our international partners. It's just a very special group of people.
Yeah, and I echo what Bill said. It's really difficult to choose a special moment. I think we are so lucky. I mean, I have in my memory the Canadian instruments. I remember our cryo testing in Canada. I started working in 2006 on James Webb. So that cryo test, and I remember going cold and taking the first picture on those detectors and being super excited. And everybody, the joke at the time was, you don't go out much, right? Because you're so excited about this. But that was such a long time ago. And then when we did the cryo testing at Goddard on the chamber with the instruments, it was special again. Johnson was special. Northrop was special. Being here was special. So everything Bill said, I think we are so lucky. And I also feel we are a big family. And the international collaboration is so great, you know, to see all of us from different places, different backgrounds working together, and we know each other, and it's a really great environment to work in. So
I tell folks all the time, this is such a special program in that there's been so many special things that you're not going to see again unless you work another program that's on the order of this size. When we were watching the shipping container go on the ship, I was talking to one of our science writers, and he's a young guy, probably in his 30s somewhere. And I said, you know, in your career, you still may not see, you got a lot left in front of you. You may never see something like this again, where this is how we move around our telescope. We were too big. We couldn't get into a C5. And even if we did, down at the launch site where the landing strip was, there were 7 bridges we had to go across to get over to the launch site. And those bridges could not withstand the weight of JWST combined with the shipping container and all the other equipment that goes along with it. It's amazing. We had to unload 38 trailers, you know, the tractor trailer trailers of equipment down at the launch site that we had to bring with us, not just counting the big shipping container with the big prize.
Right.
And now we're already starting to worry, okay, now it all has to come back. So where are we going to put it at where I work at Goddard Space Flight Center? Where's a parking lot we can sit all this stuff while we unload it? We already have other missions here at Goddard who want some of that equipment. Some of it will go into storage, and it's what do you do with all that? So it's all the logistics with this telescope has been amazing. Just moving it around the country when we've had to move it.
Yeah, didn't the mirror assembly have to also go by boat to California?
No, at that point it still fit inside a C5.
Okay.
And so we went from Goddard down to Andrews, Joint Andrews Air Base. I was going to say Andrews Air Force Base, not called that anymore. And then from there by C5 to Johnson, from Johnson C5 or Houston C5 out to LAX, and then by truck down to Northwest facilities. One of my special transportation moments was the first time, I can't remember if it was the back, I think it was the back plane coming to Goddard, landed at Andrews, and they brought it around the DC Beltway. And I was out someplace, and I pulled up Google Maps, and here's this red line going around the Beltway. I said, oh, look, there's JWST causing a traffic jam.
There's plenty of traffic jams on the Beltway to go around. I'm sure JWST wasn't too many.
But this was a special one.
Special traffic jam.
That's right.
Was the drive with the truck that just when they loaded it on the boat sort of done in secret, so to speak? Nobody else really knew it was moving.
No, because you have to draw permits. There are no markings on it. If you notice, like the picture of the shipping container, no markings.
Yeah.
There's no markings on the boat, even though a lot of folks had figured it out. There's only 2 ships that ESA uses. One of them was bringing rockets back and forth.
Right.
So it wasn't hard to figure out. It didn't take a rocket science to figure out which one was sitting out out off of Long Beach, waiting to come into. We shipped out of Naval SEAL Beach. It's a naval weapons station, which was great because we had built-in security. We didn't have to worry about that. We didn't get involved with the back of ships sitting off of Long Beach. Once we did get a couple of days out, they did turn off the tracking on it, so you couldn't track it for a while. But then that had to be turned back on going through the canal for safety reasons. And then once we got a day or so outside of the canal, we got turned off again.
Even without markings, I would have come out in the middle of the night if I had been in California just to sort of watch it go by.
Oh yeah, it was very cool. The truck left Northrop, was supposed to leave Northrop at 10 o'clock. at night. We had a few issues and just getting it out. And at one point, the truck had to do a 3-point turn that it didn't expect, and it must have taken, the driver was excellent. It took him about 45 minutes. We had to actually remove the stop sign so he wouldn't hit the stop sign. We didn't leave Norfolk until about 1 o'clock in the morning.
Yeah, I never thought the truck driver could do that turn. You know, when they said he had to do that, I think we were all like, there is no way, no way. He did great. It was amazing to see.
Begonia, I see there's actually some action. There's a worker in the clean room behind you, but he just went down below the window. So.
Yes. they are still working there.
We work 2 10-hour shifts a day while we're down there.
Yeah.
Okay.
And then when we do the electrical testing like we're doing now, we are working 24 hours just to fit everything in the schedule. And similarly, when we do the cryo tests, once you get the chambers that cold, etc., you are working 24 hours a day for 7 days a week. We have 3 shifts, and we did that for 3 months and a half to fit everything that we needed to do in that precious time when we are cold and we are duplicating the on-orbit conditions. So.
Yeah, and I would imagine you're going to have shifts then once it's in operation.
Yeah, we work around the clock for at least the first year, and then eventually, the goal is, depending upon how every satellite has its own personality once it gets on orbit. If this one behaves itself, the idea would be eventually to go to, I think, basically it's either a 5 days a week 8-hour shift, 5 days a week 12-hour shift. Which is what most satellites do nowadays. They don't work around the clock anymore.
Right. Then you just have a powerful alert system for any time it.
Oh, yeah, you get an alert system, and you go in.
Yeah.
Yeah, you can load all the visits that you want to run on board. So then it runs autonomously, it's designed to do that, and then you have safety items on board, right? If it detects something it shouldn't, it will, quiet down, stop gracefully and wait until you are in contact, so we can see what will have been the problem. So if everything goes well, it is designed to do that. So.
Yeah, and like Begonia said, if it finds it has a problem, it will safe itself until the ground gets there. Also nowadays with ground systems, through the appropriate security links you have, you can actually get on your laptop at home and pull up the telemetry pages and start looking at it at home. You don't even have to drive into the office.
That's true. Yeah.
So you can control it on your phone.
Yeah, not quite.
Now with the distance that it's going to be past the moon, can it then have direct communication with Earth? I just realized.
Yes.
Yeah.
We use the Deep Space Network for communicating.
Yeah, great. That's a fantastic network. I love it because you can look up that on your phone and always see what it's talking to and who's talking to it.
Yes. Yep. We've used it a couple times during our mission simulations.
Nice. I just can't imagine how exciting it is for you guys right now. And also just how fulfilling it is to probably work on a project like this and see it get to this point. Launch is December 18th, right? So 3 months, just under 3 months.
Yeah, and we'll be deploying the sun shield on Christmas Day. Doing it takes multiple days to deploy the sun shield. That's one of the days we work. The spacecraft knows no holidays, so we will work right through the holidays. With folks coming in, we'll have folks here from California supporting us. So it'll be it's an exciting time. It'll be even more exciting when all the deployments are done. Then we go like this and wipe the sweat away.
I suspect there's going to be a lot of scientists with family members who are like, what are you doing? It's Christmas. Why aren't you with us? And they're like glued to their computer watching for updates on the sun shield.
Yep. Yeah, it's going to be quite exciting, and we're all very confident that it's going to work. We've done everything you can do on the ground, from testing, engineering audits, environmental testing, everything we can do. We're very confident at this point where we are.
Well, I can imagine that the viewers have submitted a ton of questions and are eager to get access to you guys. Ross, how's that queue looking?
Oh, yes, the queue is looking very queuey right now. Over the course of the show, y'all, with the Virtual Astronomy Live, you always have the opportunity to put questions into chat. And if they're talking about something and you have a question about it, you can ask that at any time during the show. And I gather all the questions together today from 4 different places, and now I've got an entire computer monitor dedicated to the questions that you've put in. So, Bill and Begonia, y'all ready for some questions?
Sure.
We are.
Don't sound too excited about the questions, Bill. Jeez. Sure. So let's start with this one, and it's from J. Martin Leo over on Twitch. Will the James Webb Space Telescope ever be used to do any science of our solar system, or is it just for distant stars and galaxies? Is there a range where it's just too close?
I'll let, since Begonia has more of the science background, I'll let her answer.
So no,
I
it
don't
can
think
be.
I'll let her answer.
Yes, it can observe our solar system, and in fact, there are some of those programs that we'll mention early days will be to see, either Jupiter or Saturn or any of the planets and the moons in our solar system, or comets or asteroids. So yes, of course, on the solar system, you might not see them all the time. So a lot is going to depend, once we launch, when they can be scheduled. But yes, looking near home and then looking far away.
So I got to ask, like, the follow-up question on that. If you point the telescope at Jupiter, do you get like this? Here, I actually have a 3D printed moon on my desk. Do you get like a view like this that's mostly just one little sliver of Jupiter, or can you see like all of Jupiter and like really see I don't know, the rings of Saturn or something? What do you see? Is it super zoomed in?
It depends what instrument you are using, but yes, you will see them very clearly. That's one of the reasons you want to do. But you bring something very interesting, which is, we mentioned before that we have an instrument that's guiding, right? And that guiding instrument needs it needs to find a star and keep the star there all the time, tell its position. So one of the things we do during the commissioning is we are going to observe one of the big planets on our solar system, Jupiter or Saturn, and see how close we can get it to the science instrument before the light floods the guider and we are not able to guide anymore. So we have some modeling to know, we think it should be able to get this close. So there is certainly things under the hood that you have to do to observe nearby compared with what you do when you observe far away.
Yeah. So you say the light floods the guider. You mean like, you're looking at Mars or something, and Mars is so bright that it's too bright for the guider to look at? Is that what you mean? Or
right? If depending where it is, it might be so bright that then the guider doesn't see the star it was trying to track to keep the observatory pointing. So then you will lose the stability. We wouldn't be able to guide if it's too bright. So you have to check that background. It's as if you're looking, I don't know, taking a picture and you have a light source that becomes very bright, and then your picture, you cannot see it anymore. So something similar to that. So we do have all these things in the plan to make sure everything works. So.
Makes sense. And let's talk about that for just a second. The guider, like when you're up in space, it's not like, James Webb has a cell phone and it has like GPS on its cell phone and knows kind of where it is all the time. James Webb will point itself by looking at the stars and saying, well, here's this star and here's this star. Is that how that works? Or how does James Webb know where it's even pointed?
Very similar to Hubble. I'll let Begonia go, but it's very similar to Hubble.
No, go ahead. We have star trackers that do the star trackers will take us in the rough position where we need to be in the sky.
Right.
But they do very well pointing. But then for the science instruments, the images and the spectra, we need to be very steady. So then the way it works is an instrument will say, I want to look at this object. I want to look at this star or this galaxy. There is a catalog available. You look where the guider is going to look, and you're going to find a star. And then the guider is going to find that star, and is going to give the position of the star often 16 times every second, very accurately. And that information goes to what is called an attitude control system that has a mirror that can be moved. So if it seems that the star is moving too far one way, it can bring it back. So this happens autonomously all the time once we engage that guidance. And then it keeps the observatory really steady, and then the science instrument can go and do whatever science they need it to do. Take the image, take the spectra, etc., and we just keep it as steady as it needs to be.
As steady as it needs to be. Gotcha. Let's see. So that was like one viewer question, and then I got to ask 5 questions. So let's get some more viewer questions. But that's how it works. Like one question makes you think of another thing, It's such an interesting problem to solve. How do you put this piece of equipment into space and control it and use it to do science? Here is one from YouTube. Kuiper's Cat Astronomy says, any chance of amateur astronomers catching James Webb Space Telescope zipping past the moon? In terms of the trajectory, will amateur astronomers be able to look up and see James Webb somewhere?
No, I don't. No. I mean, first of all, we don't publicize the trajectory, and once you get out to, we actually had some discussions internally. We were just sitting one day and said, okay, could you take Hubble and actually see it out of L2? And the answer was still no.
Really?
And actually I was just reading this fact someplace today. When Webb is out at L2, we are 10,000 times fainter than the faintest star that you can see with your naked eye.
No kidding.
If I said that right.
So even, you have the sun shield there, and the sun shield is supposed to protect the telescope from the heat because you need to keep it super cool like y'all were talking about. But even that reflective sun shield reflecting back as much sun as it can, it's still, you said 10,000 times fainter than what we can see with
you're a million miles from Earth.
Yeah.
JWST is big, but it's not that big.
It's not that big.
Where you can see it a million miles from Earth.
Gotcha.
Hubble you can see. I mean, Hubble's low Earth orbit.
Yep.
You can see that go overhead. You can see the space station go overhead, as well as other satellites and so forth, but not deep space satellites.
Gotcha. So I'll put it as a challenge to amateur astronomers. If you're still watching, send me a picture. If you were able to take one, maybe. Before it gets. Yeah. Exactly. But maybe before it gets out there or something, when it's still a little closer to Earth, but then it won't be all. Well, actually, I don't know when it's going to deploy the sun shield. Does it do that once it gets there?
No, we start deployments shortly after we go past the moon, and the sun shield is the first deployment. There's some radiators that pop out with it and so forth, but we start that. So figure about 2.5 days after we launch.
Okay.
And also, you're talking about imaging it or looking at it. It's a moving target. We don't sit still and for pictures.
Yep.
Heading on out to L2.
Orbits don't work that way. If you want to be in orbit, there's no sitting still, really. Well, I guess until you get out to the Lagrange point, but whatever. Then you still got to move around a little bit, right?
And we do like a figure 8.
Yep, a figure 8 around it. Gotcha.
I think it was from NASA, but I love the idea of thinking of it as a million miles past midnight, because it's still always going to be on the side of the Earth that's dark because it's keeping the sun behind it. Mm-hmm. And it's a million miles out there.
Yep.
Gotcha. Let's see here. How many maneuvers will be required before it's in a stable orbit around L2? Is it you just get tossed out there and you just got to slow down once you get there? Or are there a bunch of little corrections?
We do our first course correction maneuver towards the end of the first day, about 13 hours or so after launch. That is the big one. Yeah. And that's all dependent upon, the rocket do a really good job and get us set. If it is, it's a small course correction. Otherwise, it could be a larger course correction.
Yep.
If required, we'll do another one on the second day. That will get us out to L2, and then we use we have to do some other not course corrections, but get ourselves into that figure 8 orbit, and then periodically we'll have to do some firings just to maintain that orbit.
Just to maintain the orbit, gotcha. So it's almost like you have a capture maneuver, I guess. Like once you get out there to L2, you have to slow down so you don't just go flying past it. You sort of have to capture yourself.
Sort of, yeah.
Right?
It's a good way to describe it, yeah.
Yeah. Gotcha. So
Can I do a follow-up now on you,
yes,
Doc?
yes, absolutely.
How much, like, what's the design life for the propulsion or the fuel that you have on board in order to keep it stable at L2 or keep it in that orbit?
We have 10 years of fuel. We also top off the tank. If the course correction goes well, and if our flight ops teams do a really good job of managing that fuel consumption for just maintaining that orbit when we get out there, you can probably get up to 13 years, maybe a little more out of it.
Gotcha.
And then we've also, we're not serviceable like Hubble,
Yeah.
but we have put little targets around. Think of it where the gas cap is.
Yeah.
That a robotic mission could go up there and grab onto the launch vehicle interface ring, and actually refuel it if they can come up with the technology 13 years from now or whenever they want to do it.
To get out there and gas it up again, huh? And that
Yep.
goes right into another question from Hydra. Is helium considered a factor in the lifespan of James Webb, or is it purely the fuel?
What was the first part? Is here?
Yeah, helium. Do you use helium on James Webb, and is there a possibility of running out of helium before you run out of fuel?
Without the cooler.
Yeah, it's.
So
Go ahead,
yeah, I
Brianna.
think it's what you said, right? I think we think the limiting factor is going to be the fuel to keep us steady, keep us at L2. But then one of the instruments, maybe that's what the viewer is thinking about. One of the instruments, Bill had mentioned it a while back. One of the instruments gets a bit colder than everybody else. It goes almost to absolute zero, only 6 Kelvin above absolute zero. And it does that because it carries its own cooler on board.
Yeah.
So I wonder if that's what the question is about, right? So that will affect, if that runs out, that affects that instrument.
That instrument.
Of course, it will be a very sad thing for James Webb. That instrument merely is the one that allows us to see up to 28 microns, so a little bit further into the infrared. So if that one runs out, then we will lose that capability. But the rest of the instruments and James Webb, we will still continue providing the rest of the fuel for the spacecraft is good.
Gotcha. So if you run, I mean, you have to use the fuel to sort of do station keeping to stay where you want to be, but the helium is just used to cool the one instrument. So if the helium runs out, it's just that one instrument versus the fuel.
Right.
The whole telescope needs the fuel to stay where it needs to be. Gotcha. Lots of good questions here. There's no way I ever get to all the questions, but I'm trying to get as many as I can. Here's a good one. Will static be a concern during unfolding? And I guess they mean like static, like, shuffle your feet on carpet or rub your hair on a balloon static.
No, it's not an issue.
Not an issue. So the sun shield unfolding isn't like rubbing a balloon on your hair or anything.
No.
Probably designed that way. Yeah. Will the telescope have any cameras showing it unfolding or to check it from an engineering perspective? Or is it just sensors?
No.
Like once it clips, like tab A goes into slot B, you know that it's going to push a little sensor and you're deployed.
It's all based on sensors and telemetry coming down. We looked at it even before I came on the program. It was looked at. It wasn't practical.
Yeah.
Plus, almost all the deployments occurred during the night. So now you have to look at putting lights on it.
Yep.
There's other issues associated with that. So it is based on sensors. Now all the telemetry that comes down, we feed actually into a graphical system.
Right.
So that in the control center, we can actually watch what's happening on orbit through an animation.
Gotcha.
We are going to have some cameras, and it's the first time they've done this, in the fairing on the Ariane 5.
Oh, really?
So you can actually be able to see the last images of JWST as it's heading out to L2 when the fairing separates, and then when we separate from the upper stage.
Very cool. I think the question comes because people like to watch live streams, and I'm not going to fault them for liking to watch live streams. Thanks for watching right now. But everybody loves live feeds, but it's sensors. Like you'll know when the sun shield is locked into place because sensors, like little things will get tripped, and you'll say, yes, all the sensors have tripped.
There's thousands and thousands of pieces of telemetry that come down from the spacecraft that we use to monitor.
Absolutely. Let's see here. We knew that this one was come up. We actually talked to this one in advance, but we heard all sorts of stories on social media about apparently pirates were going to try and steal the James Webb Telescope for themselves. I don't know what they would have done with it, but is that a for
I'm not
real
even
thing?
sure where. I know where the rumor started. It started over in the UK.
Okay.
But I don't know where they said they heard no one in the project ever mentioned it. Before we shipped, the Department of Defense has a transportation to do threat assessments. We had multiple threat assessments done. Everything was very low threat assessment. We were an unmarked ship. Like I told you, we turned off the tracking at various times.
Yep.
So the best thing that came out of it was a joke that said we're going to propose a new ride to Disney with pirates of the universe with boats that look like JWST sailing around through it, you know.
So no pirates on the high seas. You weren't going to have like an old sailing ship come up and try to steal the telescope, or I don't know, Vin Diesel trying to steal it as it goes around the Beltway or something like that. This is not something that we were actually concerned about, right?
Right.
Gotcha. We knew that one. I knew that one was going to come up. Let's see here. This is a good one. And this is actually from some of the other space probes that we know about. Like a New Horizons had to actually balance itself by adding some little knickknacks in places, right? I think there's a quarter on there and that sort of thing for the center of mass for the spacecraft. Are there any secrets like that on James Webb where there's, somebody put a commemorative quarter in one corner because you needed 3 grams of mass? I don't know how much a quarter weighs, but
No. Let me put it this way. There's none that the project manager knows about. Begonia might know some, but there's none that I know about.
Begonia, can you turn around and see if you spot anything that maybe Bill doesn't know about?
No, I think Billy's okay. I don't think there is anything there he has to worry about.
Excellent. The thing there was... Go ahead.
Is there no place where the workers have scribbled their names?
No, because well, first of all, you scribble your name. You're using a marker that could have contaminants. So you got to worry about that. But what we did, because of the over 20 years and 10,000 plus people, I didn't feel it was fair to say, okay, here's this group that's working on it now, and that's the only signatures that would go on a microchip or whatever. But what we are doing is putting on a plaque that's made out of the MLI, which is the Kapton that we used for the thermal. You can see all this shiny stuff on it.
Yep.
That actually will not be seen. It'll be covered up, but it has a dedication to the team written on it. We'll take a picture of that, and then the members of the team will get that picture.
Very cool. All right. Again, y'all, if you have questions, just put them into chat for us. You can just say question. If you say the word question somewhere, it'll come up. I still have quite a list here, though. So here's one from Kesiak asking, what are the long-term plans for James Webb with regards to any specific targets or areas that they want to observe? Is there like a backlog of 1,000 proposals for things to look at with James Webb that people have already submitted, or how does that process work?
As I kind of mentioned earlier, they go through a proposal, for lack of a better word, competition.
Right.
Every year for each cycle. This past year, we were 4 times overprescribed.
Wow.
Those that did not get selected don't get put in a queue. Those folks would have to either recompete, resubmit it, modify it. They may learn something, the first year of operations, and somebody may say, "Oh, look at this! I know here's some new things that we can do." That's one of the beauties with Hubble. With any of you learn, and as you learn, you then use it different ways.
Yep.
And everybody always says, what's the most exciting thing you're going to look at? But a lot of us have the same answer. It's the things that we don't know that we're going to find.
Yep.
With Hubble, it was, black holes was one of them. It's that kind of excitement. You're going to find stuff like that with this telescope.
Gotcha.
So it's really the unknown things that can build up a lot of excitement and really let your imagination go.
That makes a lot of sense. Like you sort of get up there and you learn what you don't know. The stuff that we already know about. All right, we already know about that, but let's get up there and see what we don't know, and then use James Webb to learn more about it. That makes perfect sense. Right. Really good question there, Kesiak.
Is there going to be a proprietary period that whoever the observers get their data, and then after that it will go into a public archive?
For the early release observations, if I remember correctly, there isn't, because they're early release. They're the things that we want the public to see right away.
Yeah.
But for like the cycle 1 proposals, there is a period of time, and I forget, I want to say it's like 6 months. That's proprietary, and then it gets put out to the public.
Very cool.
Right.
Gotcha. Here is one, and I think I know what drives this question. This is from J. Martin Leo. Will James Webb be able to capture greater resolution of exoplanets around star systems? And I'll explain that, I think, for a second, because every time somebody says they've discovered some new exoplanets, the lead image is somebody's rendering of what they think it looks like, right? So it's never a picture. It's like, here's a picture of the surface of a Kepler B or whatever, right? It's never a picture. It's always a rendering. But James Webb isn't going to be taking a picture of the surface of exoplanets, correct?
No, I mean, I'll let Begonia talk about that.
So James Webb is going to look for planets around other stars, right? And the instruments have certain ways of doing. They have something called a coronagraph, where you can cover the star,
right?
So you don't see the light of the star, and then you can pick up the objects around it, and it will be a tiny thing, but you will see that there is a planet there. So that the instruments can do it in different ways. Some of the instruments are, one of the instruments nearest, for example, is special, does very well looking for planets close to the star. I think you know when the first planets were discovered, which was very exciting, exoplanets. At the beginning, we were only able to detect the big ones, right? You were looking for a dimming of the light of the star, and it was amazing that they were found, but they were normally large planets, and we were saying, well, there is probably no life there, right? Because we know on the Earth, Jupiter and Saturn don't have it. But now the amazing techniques of the astronomers have found planets in this Goldilocks zone, right, where the Earth is. And James Webb has some of the instruments that can be looking for there, right, looking for exoplanets. But then the other thing, as we mentioned before, is looking at some of the planets we already know, and James Webb can take a spectra. So it will be a set of lines, a spectra of the atmosphere of those planets.
Yep.
But that will tell you what do you see on that atmosphere. And I know, because I was checking one of the ones that I'm excited about. I think people know the TRAPPIST system, right? That has seven planets around that red star. And it is one of the, James Webb, it is going to be looking at that particular system as one of the proposals. So I think lots of very super cool, interesting science is going to come. And as Bill said, as we start getting the data and learning more how to use it, I think it's just going to be even greater.
Gotcha. And y'all, real quick, if you've ever heard of the Goldilocks Zone, but when you use the term Goldilocks referring to a planet, it's a spot where the planet is in a specific distance away from its star, that it's not too hot and not too cold, it's just right. Right, and so it's referred to as the Goldilocks Zone.
Exactly, yes.
And I think it's sort of tied, like for our understanding, to liquid water, like temperatures where liquid water can exist in a liquid state, because that's what we know. Look at Earth; it's a big blue marble, right? And so you use the term Goldilocks Zone. Not everybody might know what that means, but it's where it's not too hot, not too cold. It's just right.
Yes, you said it perfectly. Yes.
Let's see here. We've got, here's one. Okay. Driz asking, more looking closer to home again, can James Webb be used to hunt for Planet X? So we know that James Webb can look at targets closer in, Jupiter or something like that, but could somebody propose, let's point it where we think gravity says Planet X should be?
I think they should send that proposal right in, and as Bill said, submit it and see if you get it. But it will be looking at objects in our solar system, asteroids, etc. So, who knows, right?
Who knows? Driz, if you want to write a proposal there, send it to, I guess, proposals@jameswebb.science, or I don't know what the email address is. It's something like that. There's probably a process to go through if you want to propose that as a target.
Yeah, there is.
Yeah. This is actually a real quick question that I could not Google the answer to. From YouTube, V-Man's channel asked, what time are they launching James Webb? Like time of day? Is it a night launch or a day launch?
No, it's a day launch. Down in Peru, it'll be at about 9 a.m. local time.
Okay.
Peru does not do daylight savings time. So if you're on the East Coast, they're about 2 hours ahead of us. One for launch. Right now they're 1 hour, but at that time, because we'll be off of daylight savings time, they're about 2 hours ahead of us.
2 hours ahead of Eastern time. Okay.
So it'll be 9 o'clock local in Peru, 7 a.m. East Coast, mighty early on the West Coast.
Gotcha. I see. I like those sorts of launches.
You all have to wake up. Everybody has to wake up, obviously, to see the launch.
To see it, yeah. Let's see here. There's another question here about the fuel, and it's if the fuel does run out, how long do you think you could continue to get useful images from wherever it ends up pointing? I guess it's really important to keep the sun shield shielding the sun, and the fuel's important for that, right?
We don't use the fuel to point at targets. We
Right.
use combinations, just like again like Hubble. You use momentum management, so you use reaction wheels, which are wheels that spin as you change the speed, you change the momentum.
Yep.
Gyroscopes, fixed-head star trackers, the fine guidance pointers. The fuel is only used for maintaining our orbit,
Gotcha.
and that's why you can. But once that fuel runs out, if you don't have a plan to have gotten up there to refuel it, after a period of time, we will fall out of that orbit, and at that point, we begin to lose control of it.
Gotcha. So the fuel is just for like orbits of velocity changes when you need to accelerate in a direction and maintain your
It's
orbit.
it's all orbit maintenance.
All orbit maintenance. And you said they use reaction wheels as a physical way to actually point the telescope. For people that don't know what a reaction wheel is, I don't know. Some people are sitting in an office.
Think of this,
Yeah.
and if this is spinning at a constant speed,
Yep.
if you change that speed, you're going to build up momentum, especially in a zero G environment.
Yep.
So our algorithms figure that out. Speed the wheel up, speed it back down to where it stops. You use our gyros to tell where we're pointing. You then use your trackers, your fixed-head star trackers to get a better course pointing. And then, like we're going to describe earlier, the fine guiders to get you zeroed in on the target that you want.
Gotcha. So the reaction wheels, y'all, if you don't know sort of how a reaction wheel or the station uses control moment gyros, which are like fancier reaction wheels. Yeah.
Type of thing, yes.
Yeah, exactly. But if you don't know what that is, some of you are sitting in an office chair, right? And if you put your arms out like this and you sort of do the twist, your chair goes in the opposite direction of your arms. And if you have an action like in one direction, you can get an action in another direction. You sort of move one way and it moves the other way. You do it with speeding and slowing them up. So if you've ever done the thing with the bicycle wheel and you spin up the bicycle wheel and you try to move it, or you speed up the bicycle wheel, you slow it down, and you can sort of get some momentum from that, or I guess you get some force from that. It's not like a rocket engine on the side of the James Webb that turns it in a circle. It's just speeding up and slowing down those reaction wheels. That's also part of our workout here on the live stream. Get some blood flowing by doing the reaction wheel shuffle there, the twist. Let me see here. We've got the time. We've got that. Here is one last question. We got time for one or two more questions here. This is another one from Kesiak, who asks, could there be any crossover with the Lucy mission? Like if Lucy sees something interesting once it gets out there, could James Webb turn and look at it? Or probably that's the direction it would go, not vice versa.
Webb, just like Hubble, has a moving target capability. If Lucy were to see an asteroid or something that we could actually lock onto and use a moving target capability, I mean, anything's possible. And like I said before, the more you operate it, the more you learn how to operate, the more you're going to be able to do with it.
Gotcha. So the same sort of thing, like you learn from everything, the entire body of scientific knowledge, and it came from this mission, it came from this sensor. It's a hole in our understanding, and you try to plug the hole by learning something new. There may be multiple missions that could help us define new things to look at. Submit your proposals, right?
Right. But there's no planned cross-correlation between Lucy and Webb at this point.
Right. Gotcha. Here is another one, because we hear this one all the time from Mars, right? And everybody's like, oh, if the probe landed, if the rover landed, get this from Mars 2020, we're not going to hear about it for 7 minutes, 11 minutes, 12 minutes. What's the delay in time to get 1 million miles out there? Like, we get information back from James Webb pretty quickly. Does it save up information and send it all, like download it all at once? Is it in real time that we get it? How do we talk to it once it's there?
It's multiple seconds, and I can't remember. I want to say it's either 7 or 13 seconds. It's one of the two that is the delay. So it's not much of a delay.
Gotcha.
We do have recorders on board that do bring the science data down in bulk, if you want to look at it that way. So the delay, it's almost real time when we're looking at, like when we're doing deployments, which is very important.
Gotcha. And then I think a lot of good questions here, y'all. I never get to all the questions, but we always have so many questions that come from so many different places. Let's have a look here. This one is about how you can point it, because we've got the sun shield, right? And the sun shield always has to sort of block the sun. But James Webb sort of is just one orientation to that sun shield. It's not like the sun shield stays here and then James Webb can look around like this while the sun shield stays level, I guess, or stays in one orientation. Does that sort of limit the targets you can pick out of the sky based on the time of year, I guess, where Earth is going around the sun?
I can start to answer.
Yes,
If you want to pick up on it.
No, it's good. I was going to comment. Yeah, I was going to comment. Once we are, from the previous question, once we are at L2, where we are going to go, then I think we have a delay that up there is minutes, about 6 minutes, I think. But I think, Bill, you are thinking about the deployments, right? When we are close,
yes,
and then
yeah.
it's very, very close. Yeah, exactly. But then the point thing, yes, so the sun shield always has to be, as it has been said, facing the sun and the Earth. And James Webb goes around the sun in the same orbit as the Earth.
Yep.
So it is true, we cannot see the whole sky. We can see that part of the sky at that time. But in a year, we do see the whole sky. So
Right.
that's part of the planning. That's part of the planning that you have to do when the observations are chosen and the proposals. They are slotted. When are they visible and which ones per priority? So they will be allocated. So if you can wait the 1 year, we can point anywhere. So then we are good.
Gotcha. And it just comes down to the time of year, like where the Earth and consequently where James Webb is in the orbit around the sun, because you can't look like through the sun if you want to see something on the far side. You look away from the sun, and then another part of the year you look away from the sun. But that's a different quadrant. That's a different part of the sky that you can look at it at that time of year, right?
Mm-hmm.
Exactly like
Right.
that. Yes.
Gotcha. All right. Well, as always happens, every time we do one of these shows, we have come to the end of the show. I still have a couple questions in the queue. I was trying to pick as many random questions as I could, but I did not mean to miss any specific questions. If we didn't get to your questions, there's all sorts of opportunities to do things like this. I know the James Webb team is active on social media. There's other live stream events that are going to be coming up, especially as we get closer to launch. So there's all sorts of different ways that you can keep up with what's going on with James Webb. But that is going to bring us to the end of our show for today. So I want to say a massive thank you so much to our special guests today, Bill and Begonia. Thank you so much for taking time out of your day to hang out with us and talk about James Webb.
Oh, no problem. Thank you very much. It's fun.
And
It was a pleasure. Thank you.
absolutely. And Begonia and whoever else is helping out there behind the camera, because I know there's probably some people helping out. Thank you all so much for going above and beyond and letting us get a live view of James Webb there out the observation. I didn't expect that. I thought you were going to be in an office somewhere and a blank whiteboard. Oh, look at this.
I didn't expect it. I didn't expect it either. So I, like you, thank the team that you cannot see for making this possible.
That is absolutely fantastic. And even voice controlled cameras there. Look, it's pointing at James Webb itself. So
Yeah.
thank you so much. I did not expect that. I thought you were going to have an empty whiteboard with a crude drawing of James Webb on it or something, but you've got a model back there and then an actual telescope. Just thank you so much, Begonia, and the people behind the scenes, because I know people behind the scenes. We appreciate you too. Thank you both so much for the time today. And then Summer, of course. Summer, thank you for joining us. It's always a good time to sit here and learn about a new science topic with you.
I completely agree, and I'm sorry you have to put up with my kitchen because it's not.
You need to put together like a VLA dish out of paper mache or something, and just put it back there.
I can actually. Well, I thought it was it's conflicting topics,
Oh.
but I could wear this next time.
Is that a hat? Why do you have a? Find out next time on the next Virtual Astronomy Live why Summer Ash has a telescope dish hat there. But y'all, that is the end of the show. If you want to make sure you get back to this, we do this show, and Intrepid Museum does all sorts of other shows every month. Our Virtual Astronomy Live happens on the third Thursday of the month. Been going almost 2 years now. And then Intrepid Museum also does all sorts of other cool educational shows. Historical stuff about the museum, the carrier Intrepid and its history, science stuff. We've got STEM outreach for all different ages, experiments that you can do at home. You're looking for something to do after school or something like that. There's tons of ways to keep up with the Intrepid Museum. IntrepidMuseum.org, the website. As I'm like, whoa, wait a second, did I just say the website correctly? If you just Google Intrepid Museum, it'll get you to the right place. But you can also follow them on Twitch, twitch.tv/Intrepid Museum. Some of you are watching there right now. They're on YouTube as well. Intrepid Museum's got videos and streams over there. And then Facebook. We're streaming to all these places today, just trying to get the word out to as many people as possible. But if you haven't yet, make sure you toss a follow. And if you're watching over here on my channel, make sure you hop on over and toss a follow to the Intrepid Museum on Twitch. So again, twitch.tv/Intrepid Museum. But again, Bill, Begonia, Summer, thank you all so much for the time today. We really appreciate it, and it's always a good learning experience when we do virtual astronomy lives. For now, we are going to have to say goodbye, though, and we hope to catch y'all next time. Make sure you like and subscribe or whatever we're supposed to say on YouTube. I guess we're on YouTube. And remember, the shows don't just make themselves happen. Virtual Astronomy Live supported through a NASA cooperative agreement. This is the one thing I have to read. Awarded to the New York Space Grant Consortium. I make everything else up, but that's highlighted in yellow. I got to read it. But anyways, thank you so much for the support and making the events possible. And also to the viewers, thank you so much for joining us. It would be super boring if we didn't have all those great questions every show. But for now, we got to shut it down. James Webb team has special James Webb things to do as they get ready for the launch coming up December 18th. And we will see you nerds later. Take it easy. See you next time.
Bye. Thank you.